I'm guessing you already know 3 things about Rust. 1, it's fast. Rust is just as fast as C or C++. 2, it gives you full control. Rust is a genuine systems language. It gives you just as much control over allocation and memory layout as C or C++. It doesn't use garbage collection or a runtime, and it can work without a dynamic heap. So it's being used in embedded firmware and kernels. Okay, so far this all sounds just like C or C++. Then we come to number 3. It's safe. In Rust, if your program compiles, it is completely memory safe and thread safe. You cannot segfault or corrupt memory or have use after free or even a data race. How can it do that? To have full control over memory allocation and layout, you need pointers. How can Rust let you use pointers without imposing any runtime overhead and still guarantee memory safety and thread safety? I'm Ben, an ex-Apple engineer with some decades of experience in embedded and systems level development. Rust certainly changed my understanding of what is possible in a systems language. My goal with this video series is to help you gain that understanding as quickly as possible. In this first video, I'm not going to show you any Rust syntax. Instead, I'll take you on a thought experiment where we start with C and turn it into a safe language. That way you'll understand the concepts that make Rust interesting, and you can decide if you want to learn more. I don't assume that you've decided to learn Rust, but I'm hoping you're at least a little Rust curious. Welcome. Let's look closer at these guarantees of memory safety and thread safety. There is an asterisk. These guarantees apply only to the safe subset of the language. Rust is really 2 languages, safe Rust and unsafe Rust. The delineation between the 2 is very clear. To enter unsafe Rust, you literally have to type the keyword unsafe. Doing so lets you work with raw, unchecked pointers and call functions from other languages like C. Now, at this point, I can hear you jumping out of your chair, shouting at me, Ben, a moment ago you said Rust is safe. Now you're saying safe Rust is safe and unsafe Rust is unsafe. The second I need to do anything with pointers, I'm in unsafe Rust and all bets are off. How's this any better than C? Okay, slow down. The practicality of using Rust is that you almost never need to use unsafe Rust, and that is because safe Rust has safe pointer types. These pointers are called borrowed references, and they come with 0 runtime overhead. They compile down to the same code you'd get with raw pointers, but they're checked for safety at compile time. And understanding these safe pointer types is what this video is all about. Because we have safe pointers, it's quite rare that you would need to use unsafe Rust. When you do, the best approach is to wrap the unsafe code in a module that can guarantee the raw pointers and foreign functions are always handled correctly. That module can then provide a safe API that can be used by safe client code. The idea here is that the module is extending the capabilities available to the safe language. So, for example, let's say we're making a new collection type that needs to directly access a memory allocator with raw pointers. The implementation of the collection type uses unsafe code, but that's kept private within the module. The API of the collection type exposes safe pointers, and for every piece of code that uses your API, the compiler checks those pointers are handled correctly. So no matter what the client code does, your API cannot be misused in a way that breaks the safety guarantees. And that is a huge difference from C and C++. Most of the time, you don't need to write modules containing unsafe code because the standard library already has a great variety of collection types and other abstractions ready to use. And of course, that's extended by a very healthy ecosystem of third-party packages. When you do need to write a module containing unsafe code, the Safe API puts a very clear boundary around the code you have to carefully audit. So, what are these safe pointer types and how does the compiler make these guarantees? Well, to answer that, we need to understand Rust's system of ownership. And that's what this video is about. Ownership is comprised of these 4 concepts: move semantics, borrowing, sharing, and regions. We'll introduce each of these in turn without using any Rust syntax. I'm going to take you on a thought experiment where we start with the C programming language and make it safe. So my question for you is, what is the root of all evil in C? What feature of the language enables us to write terrible bugs like use after free? Well, the answer is, of course, pointers. Pointers are very powerful. They give us control over how we organize memory. And with great power comes great responsibility. When we screw up, bad things happen. So here's a function in C that takes a pointer. From reading this function declaration, what are the assumptions that we may or may not be able to make about how this function treats the pointer? What might we find in the comments on that function? Perhaps the function just reads from the data. Perhaps it mutates fields of the data. Perhaps it expects the pointer came from malloc, so it can free the memory it points to. Perhaps it stores the pointer somewhere that will be accessed later after this function returns. Maybe even accessing the data from another thread. And what about a function that returns a pointer? When I call getFoo, I get back a pointer to a foo. Is that foo object a part of the data? If I call update on the data, will the foo pointer still be valid? Or is the foo separately allocated and I'm supposed to free it? Well, to the compiler these all look the same, so it has a simple answer to all these questions. You, the developer, are expected to read all the API comments and maintain all the interface contracts across all the interacting systems in a large, evolving codebase with different conventions across different libraries, etc. In a sense, the language is not helping us very much to get this right. It doesn't provide a way for us to make these distinctions explicit in the code. Well, there's an obvious, simple solution. Remove all the pointers. This is where our thought experiment language begins. We now have C without pointers. And I'm also going to take away your global variables. Globals are like pointers in that the data is aliased from everywhere and it's not clear who owns it. So, what do we have left? No pointers, no globals, only local variables on the stack, scalars, structs, and fixed-length arrays. I'm also going to have the compiler enforce bounds checks on array access. Without pointers, everything has to be passed by value. Function parameters and results are all by value. What does this make it difficult to write? Well, we no longer have any dynamic data structures. The language is still Turing complete, but it'll be hard to write a web browser or really anything that deals with dynamically structured input. Is it a safe language? It's memory safe. I can't corrupt memory. But I think we can go a little further. Do we still have any types that represent resources where we could have a bug if we attempt to use the resource after it's been invalidated? What about files? A file descriptor represents a resource, an open file handle. It's just an integer, but it refers to a resource held by the kernel. That resource is invalidated when the file is closed, and it's an error to use the file handle after it's invalidated. I want to take a detour here to solve this whole class of use after invalidation problems. And then we'll come back to pointers. Here we have a type called file containing a file descriptor. The name _FD is intended to suggest that it's a private field. We have a made-up API for using files. The open function returns a file, the write function takes a character to write to the file, the close function takes a file and closes it. So normal usage of the API would look like this. I open a file, I write to the file, I close the file. What if I close the file and then write to it? This compiles. I'd call it a use after close bug. What is the feature of the language that allows this to compile? Why can I close the file but still attempt to use it afterwards? There is an implicit copy that happens when I pass the file to the close function. We're passing the file by value, but really the value that's passed into the close function is a copy of the file struct. And when close returns, I still have the variable called file, so the compiler still lets me call write on it. For this file type, I'd like to prevent that copy so that when I pass it to close, it's gone. To do that, I'm going to introduce a new keyword called move. It's in all caps to make it obvious that we're adding syntax to our imaginary language. So we apply this move keyword to the declaration of the file type. That means instances of this type cannot be copied, only moved from place to place. So now when I try to write my use after close bug, When the file is passed to close, file is not copied, it's moved away, it's gone. The compiler tracks that the file variable is invalidated because its contents were moved away. The file has been consumed by the close function, and any subsequent attempt to use file produces a compile error. We can't accidentally write to a closed file because the compiler knows the file variable is no longer available. Now I want you to take a moment to satisfy yourself that this is a totally realistic thing for the compiler to do. The compiler knows we declared the file type with the move keyword. So when the file is passed to close on the second line, it records that file was moved away. So it can no longer be used. Notice we didn't change any function declarations. We just added the move keyword to the file type declaration, and that makes it impossible to copy. What if we try to get around this? This time we're trying to duplicate the file struct by assigning it to dupe, so we can use it after the close. But because file is marked as a move type, this assignment is also a move, not a copy. So now file is invalid because it's been moved to dupe, and we get the same error as before. Awesome, so we've prevented use after close bugs. Now, any issues with this? Well, you might have noticed the write function looks a lot like the close function. So if I try to call write multiple times, I have a problem. I can call write once, the file is moved into the function parameter, and I no longer have the file. So if we try to call write a second time, we get an error. The first write call consumed the file. That's a bit unfortunate. So my question for you is this: can we change the declaration of the write function so we can call write and still have the file after it returns? We're not changing the language here, just the declaration of the write function. I want to pass the file into the function parameter and get it back again afterwards. Well, what if we make the function return the file? That would be great, right? So now we can call file equals write file, file equals write file. Yeah, that would be terrible, but we have retained the property that at every point in the program, there is only one variable that can access the file. And that's important because that's how we prevent use after close bugs. We never copy the object. We temporarily give the file to the write function, and then we get it back when the function returns. You could say the write function temporarily borrows the file to operate on it. This seems like something we'll want to do a lot, so let's make the syntax less terrible. Let's invent a new keyword called borrow in all caps. I use this keyword in two places. In the function declaration, I say borrow to mean that this parameter is temporarily moved into the function when it's called and gets put back when it returns. The second place I use this keyword is at the call site. So when I call the write function, I say borrow so that it's obvious that the function temporarily gets exclusive access to the object we pass in. It might mutate the object, and any changes made will be visible after the function returns. Now, there are some rules that apply to borrowing. First, borrows are exclusive. That means while a variable is borrowed, it can't be accessed. You can only have one borrow at a time on an object. In this example, we're calling a swap function that takes two borrowed files, and I'm trying to pass the same file for both parameters. This doesn't compile because once the file is borrowed to make the first parameter, it can't be borrowed again to make the second parameter. After the first borrow, it's not available to be used at all until that borrow ends when the function returns. So, borrows are exclusive means a variable can only have one borrow at a time. The second rule, borrows must be given back. If you have a borrowed object, you can't take ownership of it and move it away. You don't own it, you're just borrowing it. In this example, I have a borrowed file and I'm trying to move it into the close function. But calling close requires that I give ownership to the close function. I move the file into close. I can't do that because I don't own it. If I could take ownership of it here, there would no longer be a valid file to give back to the caller when we return from this function. However, when you have a borrowed file, you have exclusive access, so you can mutate it. You can even swap out the whole object, replacing it with another instance of the same type. So in this example, I have a borrowed file and I create another file called temp. Then I swap the two objects, so now temp contains the original file that was passed in, and I can close it. When I return, the variable the caller passed in now contains the new file I opened. The point here is that when you have a borrowed object, you have exclusive access to it, and you can mutate any part of it, or even the whole thing. Lastly, borrows are for function inputs only. We know what it means for a function parameter to be borrowed. The borrow begins when the function is called and ends when the function returns. We don't know what it would mean to return a borrowed file from the function. In other words, the borrow ends when the function returns. This means the borrow cannot escape from the function. It also can't be stored somewhere that continues to exist after the function returns. So just a little foreshadowing, this is a limitation we will revisit, but for now this is all we know. Okay, a quick aside. We invented borrowing for move-only types, but it's useful for copyable types as well. Integers are copyable. Here's a function that takes a borrowed integer and increments it. After I've called increment twice, the counter's value will be 2. So at this point you are no doubt thinking, yes, we've just reinvented pass by reference. When we pass a borrowed parameter, we don't actually have to move anything around in memory. This can be implemented by just passing a pointer to the existing location of that variable. So a borrow is actually just a pointer type. But it's safe because these references cannot alias, meaning you cannot have multiple variables referring to the same object in memory. And these references cannot escape. They cannot be returned or stored, so you can't end up with a dangling pointer to something that's no longer there. Let's take a minute to review what we've done so far before we add any new concepts. We started with C and we turned it into a safe but fairly useless language by completely removing pointers. Then we took a step further. We realized that even without pointers, some types, like files, represent resources, and allowing those types to be implicitly copied leaves us open to use after invalidation bugs, like where you could close a file but still attempt to use it afterwards. To fix that, we invented move-only types with the move keyword. So now when you pass the file to close, it isn't copied, it's moved. The close function consumes the file, and the compiler understands you no longer have it. Then we realized we don't want the write function to consume the file, so we invented the idea of borrowing with the borrow keyword to temporarily give a function exclusive access to something. And it turns out that a borrow is really just a reference type. It's a pointer. So we have this distinction between types that are copyable and types that are move-only. Let's run through some examples and make sure we understand which column they fall into. Are integers copyable? Yes, all the scalar types are copyable. They're value types, just plain old data. It's fine to copy them because they don't represent a resource, just a value. Is our file type copyable? No. We've declared it with the move keyword because it owns an open file descriptor, and we want to make sure there is always a single instance that's responsible for that resource. How about other structs? Here's a struct called point containing x and y coordinates. Should that be copyable? Yes, sure. It's just a value type. It doesn't have responsibility for any kind of resource that we need to manage, so copying it won't cause any problems. And this type is not declared with the move keyword, so it's copyable. What about borrow file? First, let's be clear. Borrow file is a distinct type. It's a pointer. We call it a borrowed reference to a file. It's just a pointer with compile time constraints. So far we've only seen this type used as a function parameter, but we'll come back to that. So, should borrow file be copyable? Well, it's a pointer that has exclusive access to the file it points to. Should I be able to make another copy of the same pointer? No way, because if I did, then there would be two pointers, each claiming to have exclusive access. Borrows are exclusive, so borrowed references are not copyable, they are move-only. Lastly, what about borrow int? Borrow int is also a distinct type. It's a pointer to an integer. Should that be copyable? Integers are copyable, but should a pointer that claims to have exclusive access to a particular integer be copyable? No. Just like a borrowed reference to a file, a borrowed reference to an integer is also move-only, so that it continues to have exclusive access to the thing it points to. Borrows are always exclusive, so all borrowed references are move-only. So you can see how we now have two concepts, move-only types and borrowed references, working together to maintain this guarantee of exclusive access. This brings us to the end of the detour. We've solved use after close bugs by wrapping the file descriptor in a move-only type that can't be copied. And we've invented a safe borrowed reference type that makes it easy to work with move-only types. A file is a resource. Heap memory is also a resource. Can we do the same thing to bring back heap allocation while preventing use after free bugs? This is what we want to make safe. This is regular C with pointers. We malloc some memory, we work with it, and then when we're finished, we free the allocation. Malloc and free look a lot like open and close, and the data pointer is holding the resource, the heap allocation. What we want to prevent is if we continue to use the resource after it's been invalidated by calling free. The solution here is to introduce some library code with a type to manage a heap allocated array. This example is an array of integers, but of course the Rust standard library has generic collections that can hold items of any type. And not just arrays, but also hash maps, B-tree maps, etc. This array type is a module that internally uses unsafe code. It holds a raw pointer to track the heap allocation, and it calls malloc and free, etc. I'm using underscores on the field names to suggest that these are private fields. In reality, Rust has syntax for public or private fields like C++. So this array type holds the pointer to the heap allocation, the length, which is the number of items currently held in the array, and the capacity, which is the size of the allocation, including the currently unoccupied space. A typical strategy for a dynamic array like this might be that as you keep appending items to it, when the length reaches the capacity and the allocation is full, it calls realloc and doubles the size of the allocation, so you don't end up reallocating with every push to the array. Array provides a safe interface that cannot be misused to cause memory corruption. Array is a move-only type because internally it owns a resource, the heap allocation. If array could just be copied, then both copies would point to the same heap allocation and confusion would ensue. Making it move-only prevents that. The API provides a new array function that returns an empty array and a destroy function that consumes the array and deallocates it. By the way, I'm making destroy an explicit function call here, but in reality, Rust has destructors, just like C++. So the array is destroyed when it goes out of scope. Okay, what about a push function to append an item to the array? Well, push is a lot like the write function on our file type. It can borrow the array, so the caller can continue to use it afterwards. And the push function gets exclusive access to the array object, so it can check if there's space for the new item, and if the length has reached the capacity, it can grow the heap allocation and append the new item. The borrowed reference to the array is exactly what the push function needs to do its job. Great. What about accessing items in the array? This get function takes a borrowed reference to the array and the index of the item we want. What I want this to return is a pointer to the item in the array. I don't just want a copy of the integer because I want this to work with other item types that might not be copyable. Like, what if I have an array of files? I want to work with this array item in place where I can read it, mutate it, etc. But right now I don't have a reference type that can do this. What if this function could return a borrow? That would be ideal. If I could have a borrowed reference to the item in the array, I'd have exclusive access to it. I could read it, mutate it in place without copying it. To make this safe, let's review the rules for borrows. We said borrows are exclusive. That's a natural consequence of the concept of borrowing, if we're going to respect that some types cannot be copied. We said borrows must be given back. Again, that's a natural consequence. If borrowing is going to be useful, then the variable it's borrowed from has to become usable again at some point. And we said that borrows are only for function inputs. You can't return a borrow from a function. In other words, the borrow ends at the moment the function returns. And that was just because that's all we knew how to do at the time. What if we could extend the borrow for a while after the function returns? What if get could return a borrowed reference to an item in the array, and you could just use it for a while with some constraints to make that safe? To do that, we introduce the concept of regions. A region is just a region of code within a function, like from line 5 to line 10 in that function. So when we call get on the array and we get back a borrowed reference to an item in the array, we'll be able to use that reference for some region within the current function. The borrow of the array is extended beyond the return of the get function. And while that borrow persists, we enforce some special rules to make sure it's safe. So, to get clear on those rules, let's see what we're trying to prevent. We make a new array and we push an item into it with the value 10. Then we call get on index 0 of the array and we get back a borrowed reference to the item in the array. So, x is a pointer into the array. Then if we call destroy on the array, x is pointing into an object that is now invalidated. So at that point, if we were allowed to dereference x, that would be a use after free bug that could corrupt memory, etc. That would be bad. So we can't let that happen. What we do want to have work is that after calling get, we can work with x, we can dereference it, mutate the item's value, etc. Then only when we're finished using x can we do something else with the array, like destroying it. So the compiler is going to track the region of this function where x is in use. A region is like a range of lines of code within the function. For every function call that returns a borrow, the compiler figures out the region where that returned borrow is still in use. That region is what I've highlighted here. The borrow starts with borrow array when we call get and lasts for as long as x is in use. Within that region of the function, array continues to be borrowed even though get has returned. The fact that x is in use extends the borrow of array. Array is borrowed for as long as x is in use. What if I destroy the array and then try to increment x? Well, the region of the borrow lasts for as long as x is in use, and now the attempt to destroy array falls within that region where array continues to be borrowed. And because array is borrowed, it's not available to be accessed at all. You can't touch it because it's still borrowed by x. So we get a compile error, array is borrowed. Okay, this is really cool. We took what we learned from preventing use after close bugs with files, and we've used it to prevent use after free bugs with dynamically allocated memory. We now have a safe pointer type, a borrowed reference, that you can return from a function. Functions can safely return pointers into objects. We can have collection types that safely hand out pointers to the items they contain, and you can work with them directly in place. And this comes with zero runtime overhead because regions and the borrowing rules are all checked at compile time. This is extremely useful in all kinds of situations, not just collection types. Are there any limits to this? What if I want to access multiple items at once? Will this compile? Can I call get twice and hold pointers to both items at once? No. Because when I call get the first time, array is borrowed for as long as x is in use. And if I try to call get again, well, I can't borrow array again. Borrows are exclusive, so I get an error. Array is already borrowed. Now, this is actually correct because what if I pass the same index both times? If this was allowed, x and y would both point to the same item. There would be two names, two aliases for the same object in memory, and we could effectively break the rule that says some types cannot be copied. The compiler can't know that passing index 0 and index 1 will give disjoint borrows of different items. And in general, those indexes might be calculated from other state, etc. The compiler doesn't need to understand what happens inside the get function to check this code that calls it. It just knows get takes a borrowed array and it returns a borrowed reference, so array is borrowed for as long as x is in use. What if I don't actually need exclusive access to each item? What if I just want read-only access to multiple items in the array? For that, we're going to introduce a new concept, sharing. Sharing is like borrowing, but weaker. When something is shared, it's in a read-only state and nobody can mutate it. Because it can't be mutated, aliasing is fine. You can have as many read-only references as you like, safe in the knowledge that nobody can change the object from under you. Nobody can invalidate it while you're holding that reference. So, a simple example. Here's an add function that takes two shared references to integers. Again, we're inventing a new keyword. The share keyword is like borrow, but a shared reference does not have exclusive access. The object is borrowed in a read-only shared kind of way. To use this function, if I have two variables a and b, I can call add with share a and share b, but I can also call add with share a and another share a. For as long as a variable is shared, it is only available for reading and more sharing. In this case, the shares end when the add function returns, because it doesn't return a reference. But we can also return a shared reference from a function, just like with borrow. So now we can write a getReadOnly function that takes a shared array and returns a shared reference to an item in the array. This is just like the get function, but it uses non-exclusive shared references instead of exclusive borrowed references. Using this function, now I can have read-only access to multiple items in the array. So I construct my array, I push a couple of items in there with the values 10 and 20. I call getReadOnly with a shared reference to the array. I get back a shared reference to item 0 and I store that in X. I call getReadOnly again with another shared reference to the array and I get back a shared reference to item 1 and I store that in Y. The array is shared for as long as X or Y are in use. So when I say share array the first time, the compiler begins tracking that the array is in this shared read-only state. When something is shared, you can read from it, but you cannot have exclusive access to it, so you can't borrow it. What I can do is share it some more, so I can say share array again for the second call to get read-only. The array remains shared for as long as X or Y are in use, so only after I've called add am I finished with X and Y, so the array is no longer shared and I can destroy it. So this all works great. What if I try to borrow while sharing? I'm going to swap the order here. So now, will this compile? Well, the region in which array is shared looks like this. And inside that region, I'm trying to say borrow array, so I can call push. But the compiler knows array is shared within this region, so I can't borrow it, I can't have exclusive access to it. So I get an error here telling me I can't borrow the array because it's already shared. Okay, here's an interesting question. If we allowed this to compile, what terrible thing could happen at runtime? I'll give you a moment. The answer is this could be a use after free bug. Here's the array's storage allocated on the heap. If it's at capacity, push will reallocate and move the array elements to the new location. But X is still pointing to the old location. So when X is dereferenced, we're actually accessing whatever might have been allocated there in the meantime. And this is a potential security vulnerability. This exact thing happens all the time in C++ with iterator invalidation bugs that can blow up at runtime. In Rust, we have safe pointers with borrowing rules that catch these bugs at compile time. So, with move semantics, regions, borrowing, and sharing, we have an API for a heap-allocated array that is completely memory safe. It cannot cause memory corruption because the compiler checks the constraints on our safe pointer types. And the key constraint is that you cannot mutate while it is shared. This is a key insight of Rust's ownership system. It's okay to mutate if you have exclusive access. It's okay to alias or share if nobody can mutate, but not both at once. And this principle is often referred to as Mutable XOR shared in the Rust community. The compiler is enforcing the reader-writer pattern at compile time. At any given moment, you can either have one or many readers or a single writer. So if we have a variable x, we can take a shared reference to it, and while it's shared, we can only read from it or make more shared references to it. And only once all those shared references have ended can we borrow x or mutate x, because we have exclusive access to it. And only when x is no longer shared or borrowed can it be destroyed or moved. These rules are enforced at compile time. This is all based on checking one function at a time. We don't need any crazy whole program analysis. No runtime overhead, this compiles down to regular pointers. We invented all this to make correct single-threaded programs, but it turns out that the resulting system is completely thread-safe, because the definition of a data race is two threads accessing the same location, at least one of them is mutating, with insufficient synchronization. That requires mutation and sharing, which we just made impossible. Ta-da! Thread safety. Now, I know at this point you might be thinking, but Ben, what if I want to share mutable state between threads? Well, this is a big topic, and we'll get into it in future videos, but very briefly, borrowing and sharing give us the building blocks from which we can build a huge variety of APIs that extend the capabilities of the safe language. So for example, the Rust standard library provides a mutex that can be shared between threads. When you lock the mutex, it blocks at runtime until it can get exclusive access to the data protected by the mutex. Then you get back a guard object that lets you access the data. It's safe because the mutex enforces exclusive access at runtime. It's not possible to misuse the mutex and cause a data race because the compiler enforces the borrowing rules on the mutex API. And mutex is just one example. There are channels, atomics, work stealing queues, all kinds of options. They're all built in library code using these basic ideas of ownership. It turns out that these basic primitives, move-only types, borrowing, sharing, and regions, are incredibly useful. With move-only types that can't be copied, we can write a function that consumes an object knowing it can't be used again after it's been invalidated. With borrowing and sharing, we got back pointers that are safe because they enforce mutable XOR shared. And with regions, we can safely return those reference types from functions, with the input to the function continuing to be borrowed or shared for as long as the returned reference is in use. Borrowed references and shared references generate the same code as regular pointers, but the compiler treats them very differently. So now we can write APIs that specify the constraints that apply to the pointers involved, and the compiler can check those constraints for us. Now, I haven't yet shown you any actual Rust syntax. Of course, Rust doesn't have any weird all-caps keywords. It does have a modern type system, great package management, very helpful compiler errors, and it does away with debugging seg faults and data races at runtime. It's an extremely practical language for large projects, both for systems level code and in applications. And the end result is a greater sense of security that your software is robust because so much more safety has been constructed at compile time. Of course, catching memory safety bugs at compile time means running into new interesting compiler errors when you write code that breaks the rules. Coming from other languages, these errors will be unfamiliar. To really understand the ownership system, you need some experience bumping into those errors and fixing them. When people are learning Rust, they often talk about a period of fighting the borrow checker. The borrow checker is the compiler phase that checks the borrowing rules. Once you've internalized the rules the compiler is playing by, you'll run into them way less often. You'll be designing ahead to work with the ownership system. Rust's error messages are generally really helpful. The compiler teaches you as you go. Of course, to get that experience, we'll need to start learning actual Rust syntax. And that's where we shall begin in the next video. To help you along the way, I've created a visual guide to the Rust type system that serves as a handy reference. Just go to rustcurious.com and click on the Elements of Rust. In future videos, we'll work through each part of this table. We'll cover the scalar types on the left pretty quickly, then the compound types in the middle, and then we'll get to the borrowed reference types over on the right. You'll see how the ideas we've seen in this video show up in very practical ways in Rust. A special thanks to Aria Desires, author of the Rustonomicon. This video was based on her way of explaining ownership in Rust, and I'm grateful for her encouragement to share it with you here. So, I hope what you've seen so far has motivated you to learn more. If I've piqued your curiosity, subscribe to the channel, and I'll see you soon.